Okay, well, welcome back to the second question in the free response section of our recent AP exam. This is an interesting question where this capital H height is fixed, but this position P can kind of slide up or down to adjust H1 and H2. Obviously, big H is the sum of those things. Big H can't change, but of course, the premise here is that H1 can change and H2 can change by just simply adjusting this position P to higher or lower. And in this kind of thought experiment, there's a student who's playing around with this, and the student wants to adjust H1 and H2 to make D as large as possible. D is the horizontal distance that the block would have. Gets released up here, slides down like so, then comes off here with some kind of horizontal velocity, and of course follows a trajectory down to the ground. Okay, so that's the premise. And the very first question here says that can you explain why making H1 very small would cause D to be small, even though H2 would be large? And it says to do this without using equations. So the key to recognize here is that if H1 is small, if this value is small, then there's not much of a ramp for the block to come down. The change in the potential energy of the block from its release point to its launch point would be very small. Small change in potential energy would mean also that the gain in potential energy would be small, and so the velocity would be pretty low coming off at this point. So even though it might fall a long way, it doesn't have much velocity in the horizontal direction to stretch this value of d out, okay? And obviously in the limit as h1 becomes 0, there'd be no movement at all. So here's the kind of an answer I was looking for. I was looking for something like this. As h1 approaches 0, the change in the potential energy would also approach 0. So the increase in kinetic energy would also approach 0. This change in potential energy would be a loss, and that would, because of the conservation of energy, result in an increase in the kinetic energy. A low kinetic energy would mean a low exit velocity, and so it falls far down, but not left to right. So captures both things. It falls far down. That's the fact that H2 is large, but it doesn't travel far left to right because it has a low exit velocity, a low kinetic energy. So I was looking for those kinds of answers, okay? The second part of that is the converse. Let me just slide down there and take a look, okay? So the same kind of thing. Why would making H2 very small cause D to be small, even though H1 would be large? Okay, so now, in that case, the thinking is this. Let's go back to the picture for a second. We would drop P down, oops, sorry. We would drop P down pretty far so that H1 would be big and there'd be a giant change in the potential energy, and so a lot of kinetic energy as the ball came off of point P, the mass came off point P. But as many of you pointed out, right, as H2 approaches 0, the time to the ground approaches 0, and so there's little time to fall, which means little time to travel left to right, even though it might have a high velocity. So those are the first two. We're looking for an energy argument in the first one and a time argument in the second one. Let's go right on to question 3 here, or the next part, okay? It says to derive an equation, let me just pull this down here. Derive an equation for D in terms of H1, H2, M, and the physical constants as appropriate. So again, like in the last question, can we come up with something that would generally solve this problem? So I started by thinking about this here, where this distance d, that horizontal distance they defined, would be velocity times time. It's a horizontal velocity, so it won't be changing. And the time, which is going to be governed by gravity, will be the time of the flight. So starting from there, and I define v as the exit velocity, and t is the time in the air. So my next step was to try to come up with expressions for both the velocity and the time. So from a time point of view, I did this, okay? Uh, um, Using the idea, the second of our kinematic equations, where x is equal to x0 plus v0 delta t plus 1 half a times time squared, recognizing that the distance it would fall would be minus h2. The initial position we could call 0. The initial velocity in the y direction we call 0. And so we're just left with uh, minus 1 half g times time squared. Okay, minus because the acceleration is downward, and minus h2 because it's falling downward. The two minus signs cancel, multiply through by 2 and divide by g. We get 2h2 over g equals t squared, and so t is the square root of 2h2 over g. So that would be my expression for the time, and it's in terms of h2 and physical constants like g. So that's okay. Now I need something for velocity. I need to know what's my exit velocity. And so now I'm going to make an energy argument, okay? I'm going to say that the kinetic energy that the mass has as it comes off that point P is 1 half mv squared, where v is the exit velocity. So there's my use of v there. And that has to equal mg times h1. That's the change in the potential energy, m times g times the distance from the release point to point P. So it's got h1 in it, and the masses cancel, all right? And I'm off to the races here. V squared equals 2 times g times h1, and then v is the square root of 2gh1. So now I've got both v and t in terms of h1, h2, m, and the physical constant. So m turns out to not have an impact on this at all. Okay, I combine the two of those, and with a couple of algebraic steps, I get to the point where the acceleration due to gravity cancels, the two 2's multiply to be 4 underneath the radical sign, and so I wind up with d equaling twice the square root of h1 times h2, which is a pretty satisfying result. All right, quickly now, we should be able to look at the next part of this. Okay, so here's my result again. All right, d is equal to h1 times h2. So now we want to share the reasoning where we can support our we want to show the step in the derivation that supports our reasoning in part A1. So that was the one that said, how come making h1 would result in a small value of d? Okay, well, let's go back to our velocity idea, right? We were saying that if h1 approaches 0, the exit velocity will approach 0, and you can see that that is borne out from our calculation of the velocity, which is square root of 2gh1. As h1 approaches 0, so will the velocity. So I could add a little bit more about that, but that's the basic reasoning. The second part of that is to point out the part in the derivation that supports our reasoning in part A, number 2, which was if you made h2 small, why would d be small? Well, we said earlier that if h2 was small, the time would go to 0. As h2 approached 0, the time would approach 0. And you can see this as well. In our derivation, we had t is equal to square root of 2h2 over g. If h2 approaches 0, the time approaches 0, and that will result in a low value of d. Okay, last one, and we're done with question 2. If the experiment is repeated on the moon without changing h1 or h2, will the new landing distance be greater than, less than, or the same as when the experiment is performed on the Earth? Now, kind of banking on the idea that you think that you understand that the moon has a lower acceleration due to gravity, and that might influence your thinking. But our final result here shows that D was independent of the acceleration due to gravity. So this experiment could be canceled out. It could be carried out anywhere, and the value of G would cancel out. So the answer would be the same as, because the value of D does not depend upon gravity.